All right, next let's take a look at exercise 14.1. So this is from the chapter on Monte Carlo integration. And it just says write a script or function to demonstrate the use of Monte Carlo int.m for a function of your choice and compare it to the built-in function integral. And so the chapter goes through Monte Carlo integration and then ends with this final simple version of our code, which is capable of evaluating the integral of any single dimensional function. And so we just want to test it out. And so the problem essentially wants you to download this code. And so remember, if I click on it, it'll open up, and you can open up the code in Google Drive and download it. But you just want to use this code to compute the integral of some function and compare it to the built-in function integral. And then we could play with it further if you want. But part of it is, going through the chapter, this is pretty darn beautiful, right? So in just 3 lines of code, right, you're able to write some function that could evaluate the integral of anything. Okay, and in theory, you could even consolidate this to, 2 lines if you wanted to simplify it even more. But so if I jump over to MATLAB, all right, I have the code downloaded. Here it is, Monte Carlo int, and so I'm just going to create a script again in which I test the code out. Okay, so let me start by defining function to integrate. Okay, hey, and you know what I'm going to do since I have 13.1 open? Let me just copy this. Let me get my molar gas constant. Let's try this guy out. Okay. Since I have it, bam. Okay, so let's do this. Okay, so if I close that, and so I'm going to call this exercise 14.1. So if I run this, I forgot to copy my lines with my temperature. One more. I've got to get this. Boop. Okay, now I'm good. Okay, so now I have T1 and T2. So this is just because I had just did this. Just did this in 13.11, the video we just recorded. So this is our heat capacity equation. So we're integrating Cp divided by T. So here I am evaluating the integral using the built-in integral function. So integrating Cp divided by T from T1 to T2, and I get 20.6077. Okay, great. So let me say, now comparing to the use of Monte Carlo integration. Okay. All right, so my Monte Carlo code, I'll call it T-term MC, is going to be called this Monte Carlo int. Okay, first argument is my function to be integrated, just like integral. Second, though, I need to add an extra term of the number of random numbers I'm going to generate in order to estimate the value of my integral. So let me start with something like 1,000. So I'll type 1e3. Okay, and then the range, where the range again is T1, comma T2. Okay, cool. Right, that should be it. Oh, I take it back. X range I entered as a vector. So this actually is T1 to T2. Okay, cool. So if I save it, and now I run it, okay, using built-in integral, all right, my answer is 20.6077. Using Monte Carlo integration with 1,000 random numbers, I get 20.6538. Okay, pretty close, not too bad. And again, 3 lines of code, right? That's it. Okay. If I were to increase the number, so if instead of 1,000, I make that 1,000,000, I can change it and run. Okay. It's a little closer, 20.6077. Now it's 20.6057, right? That's using 1,000,000 random numbers. And again, just that simple function using 3 lines of code. Okay, so that's all I wanted you to do, right, for the solution. But since I'm recording the video, I'm going to do a little more. So what we also looked at in class is we generated a plot looking at the effect of the number of random numbers, or the number of samples, as a function of the value of my integral, and then we plotted it. And what we're going to show, or what we want to show, is what'll happen is we'll converge on the solution, but you're going to continue to oscillate around that true value, right? So, even if I run this for, billion, right, I'm not going to get that exact answer, right? More than likely, yeah, I could get the right answer, but as I increase n, you're just going to have some fluctuations around that true value. Okay. But let's take a look at it. So what I'm going to do is let me make this a little bigger. Okay, and so I'm going to comment that out for now. And so I'm going to say looking at the effect of n on the computed value. Okay. So let me create this in terms. I'm going to create a vector for the number of terms I'm going to use. And I'll go from 1 to, oh boy, what do I want? I'll go from 1 to 1 to the 9. I'll go up to a billion. Okay. But I don't want to go too crazy, so I'm going to go in increments of 1,000. Okay, cool. Okay, so then I'll create a vector to store my results. So t term, and I'll start with zeros, size of n terms. Okay, and then I'm going to loop over. And so I'm going to go for I equals 1 to length n terms. Okay, so my keyboard or MATLAB seems like it has a little delay as I type, but let's keep going. So I'm going to loop over this vector of terms, and what am I going to do? T term I, the ith value of t term I'm going to compute is going to be equal to, so now I'm going to have the same call as before. Okay, only for n, okay, this is going to be the ith element of my n terms vector. Okay, and then let's plot the results. Okay, so open up figure 1. Okay, let me do this just so I can scroll up. So I'm going to figure 1, and I'm going to start by, let me do a hold on. I'm going to start by, I want to plot my reference value last, that way it's on top of my data. So I'm going to plot t term versus, nope, n terms versus t term, and we'll make those, say, black circles. And then I'm going to plot, so I just want a horizontal line corresponding to my reference value, which is this t term up here. So x, I'm going to go from, I'll just make it, I'm going to keep it general, n terms 1, comma, n terms end, versus t term, t term. Okay, and let's make that a red line. X-axis is going to be number of terms, or number of random numbers, and y-axis, that'll be value of integral. Okay, cool. So let me save that. So all I did is I commented this out, created a vector of n terms. How many random numbers do I want to use when I solve? Great. So I'm going to create a vector to store the corresponding value of my integral for that number of terms. I'm going to loop over this vector of number of terms, and for each case I'm going to calculate or estimate the integral, save it to a vector, and then I'm going to plot. And actually, first time through, let's make this, I'm going to make this a billion, just because I know a billion didn't take very long, and then we'll try and increase it and see. Okay. Actually, that's not a billion, that's a million, right, which is the last one we had. So if I just go up to a million, going to go up to 1,000,000 in increments of 1,000. I plotted. Okay. Unrecognized. Did I spell XX? Oh, it's not my x-axis, it's my x label. Okay, let's try again. So running, it only took a second. Okay. So I'm going to go from 1 to 1,000,000 random numbers in increments of 1,000. And here's the resulting figure. Okay. And actually, it's kind of interesting. So it looks like, oh, and actually, I probably shouldn't start with one term, because when I have one term, my estimate's way down here, so it becomes hard to see. So let's start with 1,000. Okay. So I'm going to have as a minimum 1,000 terms. So I'm going to go from 1,000 terms to 1,000,000 terms in increments of 1,000. Okay, here we go. This looks a little cooler. All right, so this is, oh yeah, number of random numbers, right? It's this number times 10 to the 5. So I'm going from 1,000 up to 1,000,000. And then the circle, right, corresponds to my estimate of the integral, and my black is the value that I get with the reference method using integral. All right, and so what I see is that, I get fluctuations around that true value, and as n increases, which should happen, is that fluctuation, right, looks like it's decreasing, but it looks like I get this constant fluctuation around that average. 1,000,000 didn't seem like it took too long. If I were to make this, let's go up to 1 to the 9. So now if I go to 1,000,000,000, cross my fingers and hope it runs, we can see if it decreases anymore. But that's it. All I wanted you to do is just try and evaluate the integral using Monte Carlo compared to the reference method, and you can play around with the number of numbers. Wasn't expecting you to make a plot. This is just for our own fun, if we can call it that. But let's see, I might have bit off more than I could chew now in terms of shooting for up to 1,000,000,000 random numbers. If I peek at what I had last time in terms, since it's a vector, when I went up to 1,000,000, it looks like my vector was of length 1,000. Maybe going this high wasn't a good idea. Give it one more second before I kill it. Instead of 1,000,000,000, we can make it 5,000,000. We could increase it that way. Okay, so I'm going to kill it. All right, and I look at my vector. Right, my vector is pretty ginormous. So let me, instead of making this 1,000,000,000, we can make it say 5,000,000. Okay. Or actually, let's start by 2,000,000. All right, 1,000,000 worked. Here's 2,000,000. So 5,000,000, right, was 5,000. 2,000,000 should be 2,000, vector of length 2,000. So let's see. Come on. There you go. So 2 million worked, right? And it's the same, right? This looks like large fluctuations initially, and it looks like maybe the fluctuations are decreasing as n increases. But that's it, right? So you could keep trying to increase. At that point, it's just a matter of your patience and your computing power in terms of memory. But that's it. And the big thing is there's some points in here, I'm sure, which are pretty darn close to what that reference value is. But in general, just know you're going to get fluctuations around that average. And as you can keep increasing n, right, you might get it to, the fluctuations to decrease. But right, just think of it in terms of fluctuating around that average. The benefit of Monte Carlo, though, is here I am. Can evaluate the integral using this code of any function of a single variable, any one-dimensional function or two-dimensional function. So any function of a single independent variable, right? I can evaluate using this simple code, simple 3 lines of code. No matter how complicated, no matter how complex, I'm able to make an estimate. Hope that helps. We'll see you in class.